Okay, so today we are going to finish up with the relational algebra. So today's topics: finish the relational algebra, and then go over the relational calculus. And we are going to specifically be covering something called Tuple Calculus. Okay, and I don't think it's as hard as you might think, so don't try not to get intimidated. Remember that relational algebra is more of a high-level procedural description of how to execute a query, whereas the relational calculus is a declarative means of specifying a query that specifies what you want, but not how to execute the query. And that SQL, a couple other important facts, SQL is based on the relational calculus. And also when we talk about relationally complete languages, that means that they have to be translatable into the relational calculus, meaning reducible. Any query that can be expressed in the relational calculus must be expressible in that language. And conversely, any query that you express in that language must be expressible in the relational calculus, and that makes it relationally complete. Okay, so if you see a question says what makes it relationally complete, it's the relational calculus, not the relational algebra. And again, the final thing, the relational algebra and the relational calculus form the basis for the DML, the direct manipulation language of the relational model, whereas chapter 4, which talks about the relational model, that forms the basis for the DDL, the data description language. Okay, last time we talked about the 5 fundamental operations associated with relational algebra, which were select, project, Cartesian product, which we didn't actually talk about, we will today, set union, and set difference. We also talked about set intersection, which is a courtesy operation because it can be expressed in terms of set difference. Today, we're going to talk about Cartesian products, joins, and set intersection, which are the final 3 operations in the relational algebra. So Cartesian product is what hopefully you learned in 311. It's the concatenation of every tuple in the relation R with every tuple in the relation S. And by itself, it's not particularly interesting, in part because you can see it smashes together the same columns twice if there's identical columns, but also because typically you don't want all of the tuples from both relations. You just want a subset of them. So typically you combine Cartesian product with selection. So as an example here, we are finding all students who are taking a course and their ID. So student 1 is taking CS 140 and ECE 255. Student 2 is taking CS 302. You can see we start with a cross or a Cartesian product, students with courses. From that, we're selecting students whose ID matches the course ID. So in this case, they're taking the same. Student 1 is enrolled in CS 140, whereas down here, that Cartesian product gives a student 2 being matched up with student 1 who's taking ECE 255. That makes no sense to us because that doesn't, student 2 is not actually taking ECE, well, yes, student 2 is not actually taking ECE 255. So we only want the students who are actually taking the course. We get that by ensuring that we're only selecting tuples where the student ID matches the student ID in that course. And then we project out just the student ID and the course ID. And Cartesian product and selection is actually a single operation that we call join. So it's so important, joins, that they come up with a special symbol for them. Now, joins were one of the most difficult operations to implement efficiently, and that's why in the 1980s it took a while for relational databases to be adopted, because it took researchers a number of years, almost a decade really, to develop optimization algorithms that would efficiently implement joins. There are, in fact, various forms of the join operation. In SQL, we typically limit ourselves to natural joins, outer joins, and semi-joins, but theoretically, the most general form of a join is the theta join, and then it gets more specific. An equijoin is a more restricted version of a theta join, a natural join a more restricted version of an equijoin. An outer and semi-join are kind of generalizations of an equijoin. So the symbol for the join is that kind of, I don't know, it looks a little bit like infinity, except that it looks like an hourglass actually, tipped on its side. And the F is some kind of formula which can actually be any kind of relational operator. So you could actually say join R with S where the salary in R is less than the salary in S, but typically that's not a particularly meaningful operation. And so while theta joins are fine from a theoretical perspective, we typically are only interested in equijoins where we are going to be combining based on equality. So for example, the previous query you saw where I'm listing, in this case, the name and comments of all students who have taken a course. I first project out the comment and course ID from courses. Then I join, so it has to be, the student ID matches, the student has to be enrolled in the course. That's what this equality says. And then I project out the student. And you'll notice this is a very specific procedural way to do this query. It's telling the query optimizer first do the projection, then do the join, and then do the projection. I could actually do this in a different order. I could have done the join first, then the projection, and then a second projection. So this is very procedural. Okay, and then a natural join is an equijoin where we're doing the join on the common attribute. So here, we're not necessarily joining on common attributes. Here, with the natural join, we are. They're the common attributes, attributes with the same name. And, unlike the equijoin, we eliminate one occurrence of the common attribute. So back here with the equijoin, you'll notice that the ID appears twice. The student ID appears twice in the join. Okay? Whereas here, it doesn't. It appears only once in the natural join. So that's one difference between an equijoin and a natural join as well, is the natural join eliminates one occurrence of the common attribute. And you'll notice that in a natural join, you don't list the predicate. With an equijoin, you had to list what the equality predicate was. Also with a theta join, with a theta join, you have to list the formula. But with a natural join, it's just assumed that it's an equality predicate on each of the common attributes. So here's one where we're simply joining on the student ID. It's actually just like this equijoin, but it is more succinct because the student ID was the common attribute. Okay, we saw the outer join when we were doing SQL. The outer join says that, well, the left outer join says that all tuples in R participate in the resulting relation, but that if there's no matching tuple from S, it's nulls. So, for example, if R has, let's say, the ID, student ID S03, S04, and let's say C is courses, and let's say it's ID and course ID. Maybe student 03 is taking CS 102, and student 03 is taking CS 140. And if I do a left join, which is what this symbol here, so the open part right here indicates it's a left outer join. The result of that is S03, course ID CS102, S03, CS140, S04, null. So S4 participates even though there's no S4 in the course relation. So that's the form of the outer join. And then we just did an example. I'll let you look at that later. The semi-join is when you only care about having one side of the join appear in the solution. So in this case, we only want tuples from R participating in the solution. So we join it with S, but all we care about are tuples in R. So that's similar to saying do a join on S, but take out or project out only the attributes from R. So as an example, we might say, give us the list all students who are taking CS 140. Well, in order to figure out which students are taking 140, we have to look at the course relation. But we don't want any information from the course relation in the result. We only want information about the students. So that's a semi-join because we only want results from the student relation. So we write it like you see here with a half an hourglass. And we're selecting from courses those tuples with CS equal to 140. The result is that Smiley and Pooh are taking CS 140. So that's a semi-join. Okay, so for the most part, you don't really care when you're writing a query what the join is, but you need to be able on a test to tell me the differences between these various joins. Okay, so questions about the joins. I know we covered them a lot in chapter 6, so what we really went here through was just notation. Okay? So that brings us to division, which is the operation that generally gives people the most trouble. Remember, it's kind of saying we want all people or all objects that have done all things. So it's something like give us all people who have visited all parks in Tennessee, or give us all guests who have stayed in every room in the Grand Sylvester Hotel. Okay, so again, to refresh your memory, you have two relations. So we call them R and S. The attributes in S, so call the attributes in S, has the attributes B, and in R we have the attributes A. So to do a division, we say that B must be a strict subset of A. And the result is going to be whatever is in A minus B. So the resulting attributes or whatever is in A minus B. And in order for something to appear in the result, you have to have, for some combination of values in A minus B, so for example here, A minus B is the column guess number. In order for a certain combination of, let's say the attributes were A1, A2, in order for this set to appear in the solution, you have to have that there is one tuple with the attributes from B in R. So that is, for every room that is in S, you have to have one there, you have A1, A2, AN 100, one where you have A1, A2, AN 200, one where you have A1, A2, AN 300. So you have to essentially match every tuple in S. It's almost like a more restrictive version of a join. Instead of just matching one tuple in the other relation, you have to match every single tuple in the other relation. Okay. So this is simply what I told you. There's a number of preconditions on set division. And it says S is defined over the attribute set B such that B is a subset of A, but it doesn't make sense for it to be anything other than a proper subset, because if B is equal to A, you can have nothing in the quotient. So the book says it that way. I really say it has to be a proper subset. So there's at least one attribute in this set C. If B could equal A, C would be the empty set, and set division really wouldn't make sense. So it's actually a more severe form of a semi-join, because all we care about is tuples in R. So back when I didn't really understand set division very well, I did this slide, and I still have it in here because I think it does. This is how I came to grips with set division, and it required a couple years for me to really wrap my head around it. So when I first started with it, the way I kind of understood it was, okay, I first am going to cross out any rows in R where the Z attribute doesn't match, or where the Y and Z attributes don't line up with what I have in S. So in this case, Ralph, Joe, and Mary's tuples don't line up with anything in S. Whereas if I look at the remaining tuples, you see that their Y and Z matches one of the tuples in S. So I started by crossing out all rows in R whose B attributes didn't match any row in S. Then I started with the first row that had a matching set, which was Ralph, and I would find all of Ralph's other tuples. And if, when I was done, my collection exactly matched what I had in S, then I put Ralph into the solution set. And in this case, there are two tuples for Ralph that match what's in S, so it completely matches everything in S, and Ralph belongs in the solution. Then I did the same thing for Mary, but Fran doesn't make the cut because only one of Fran's, I needed two tuples for Fran, and only one of them was actually in the S set. So, I'm sorry, only one of them was in the R set, so it wasn't good enough. So my result was Ralph and Mary. Yes?
Did you say this is how we should be thinking about it?
No.
No.
Okay, but it's a way to manually do it. Okay?
This gives you the right answer.
It gives you the right answer. It's one way to get the right answer, and it's still an okay way to get the right answer. Now I finally saw the light, which is, I finally understood, and no book really did a good job of explaining it. So it was me just finally the light bulb going on and realizing it's one of these all things. You have to, you're talking about, I want to make sure you've done something for all tuples in this other thing, like visited all parks or all states in the country or all rooms. And once I understood it that way, it became very easy actually for me to compute set division. I just went through and made sure, okay, does guest A, have they visited every room in the Grand Savetter Hotel? Yes or no? Okay. Okay. Now, here's the formal derivation of set division because it's a courtesy operation. It does not have to, it can be expressed in terms of projection, Cartesian product, and set difference. So it's a courtesy operation. So you start by projecting out the attributes that are solely in R, and you assign that to T1. So the easiest way is to look at an example. So here's R, here's S. So step one, we project out just the attributes in C, and this gives us T1. This is our potential result set. Okay? This would be the result set if everyone in R had visited everything in S. So T1 is our potential result set. Okay, but not everyone in T1, so you could also call it our candidate result set. Okay, another way is our candidate result set. But not everyone in the candidate results test will actually make it to the result. So in step two, we are going to do something unusual. We remove from R the multi-rows that match S. So what we're going to do is take the Cartesian product of T1 and S. So we're taking our potential result set and crossing it with S. So this is the set of tuples that would have to exist. T1 cross S is the set of tuples that would have to exist if every item in the candidate set were to appear in the result set. Okay? Then we subtract from this set everything that is actually in R. And what that's going to do is if someone matches everything in S, that's going to remove all the tuples for that person from this set. Okay, so think about that. Let's look at T1, I don't have it, T1 cross S minus R. Okay, we take out everything associated with A because A matches everything over here. And same thing, everything in B goes away. Okay. But when we subtract this one, we only end up removing this row from T1 cross S. So the result is that this row is left when we've removed all of R from T1 cross S. So what we have left is basically everyone who has not, I'm going to put in quotes, visited every tuple in S. So in fact, what we're left with is everyone who's kind of lacking. You can think of what's left is what they still have to do in order to make the cut. So C would still have to visit location 2 or room 2 in order to make the cut. Okay, so this is kind of gives us T1 cross S minus R is what the people who will be rejected would have to do in order to make the cut. So the final step is when we subtract T2 from T1, T2 is the set of people who do not make the cut. Therefore, when we subtract T2 from T1, T1 is the list of all possible candidates. T2 is the set of people who do not make the cut. Therefore, the result right here, T, is the set of people who do make the cut. So it's a three-step process. If this doesn't seem intuitive to you, it took like 4 or 5 years before I really got comfortable with this. So I don't expect that you're totally comfortable with this just looking at it right now. You may have to work with it. And this is one of those things where you may not be completely comfortable even when the semester is over. I just gave you my best intuitive way of thinking about it, and that's evolved over 4 or 5 years. Okay? So, questions about that? Either the formal basis or what intuitively set division represents. Okay. So, set division is also not an operation that is supported in MySQL. But there is a way that you can do it. So the way is to count the number of tuples in the divisor. So let's say that we want to find out everyone who's visited all the national parks. So we would count how many national parks are there. Okay, so down here, there's 3 national parks. So we would count how many tuples are in the divisor. There's 3. Then we want to select any attribute in the dividend, which is going to be our visits, that has the same count. So for example, is it Smiley or Brad? Is any of them going to make the cut? I don't think anyone makes the cut if it's just that. Smiley makes the cut. So if I select and count, Smiley will have a count of 3, which is the same as the number there. So here's the query in MySQL. I select the person name from visits, comma, park, where that person has visited the park. So that says where the person has visited the park. I group it by person name, which allows me to use the count in the clause here. So having count v dot person name equal to, over here I have a scalar, select count star from park. And that will give me set division in MySQL. Yes?
So with this, you couldn't see like who just visited those items.
Pardon?
You couldn't just pick 2 out of 3 with this.
I could actually have said where v dot park name equals and. I could have said v dot park name it would have been tough. The answer is yes, but I would have had to say v dot park name equals Yosemite. Actually, v dot park name in Yosemite. What was the other park you wanted? Yellowstone. I can't get it all in, so I'll say yellow. And down here, select count star from park, where park name in Yosemite. It would have gotten pretty gnarly, right? But I could do it. But I have to do the restriction in both places. Now this isn't actually set division anymore either, because set division strictly applies only when I'm saying it has to be everything.
If someone
Yes.
same car twice.
So then I would have to say probably select distinct. Pardon?
Would those technically be on set divisions just because the projection,
It's
not projection,
yeah, J as I don't know about that. I think group by is still going to group. So there would probably be a date here as well. And the problem is that makes the tuples not distinct. I'd have to think about that. I'm not going to try to. It's a good question, and I would have to. I will think about it and get back to you. It's a good question. Not sure what happens when you have duplicated visits. Certainly could create a view where I get rid of them. That would work for sure.
I mean, if the projection is itself a relation, then
Right. But in this particular query right here, how I would project it out, I'm not totally sure. I know how to project it out. I can't, what I'd like to say is select v.persons from visits, v,
select distinct
project,
person name.
right, project person name, park name, but I can't. It's, and grouping by v.person name is probably going to collect all, like if Smiley has visited Yellowstone twice, I'm guessing it's going to collect Smiley twice
If
for
you
Yellowstone.
selected distinct v.person name,
I don't, that, I want to
That's
sit,
my-
Jay, that's why I want to do it offline. I can waste probably 20 minutes. Basically, I got this one by doing trial and error. So I can spend 20 minutes here in front of you all trying to figure it out, or I could go off on my own, figure it out, and give you the right answer. I'm going to do that. You may be right, you may not be right. That was my initial impression, is do select distinct v.person name, but not sure if that works or not. So, other questions? Looks like some people are trying it. Yes?
Yeah, I'm not doing something, but in the first part it said like, why are we joining visits and park together? Because we're not using park anywhere.
I'm using it right here. So I'm restricting it to, so I have to make sure that I combine people with the parks that visited. So the reason I have to do the join is I don't want to sweep up people. I have to figure out for each person which parks they visited. The only way I can figure out which parks they visited is to join the visits with the parks. That, I think I see what you're getting at. You're saying that by itself you could just, yeah, you could simply, actually, yeah, I think you could actually say, I think what you're saying is get rid of that, group by v.person name,
you count distinct
Yeah.
from
having count, that's what you're saying, right? Why not do it that way? I think you're right. I think this is a, yeah, I think this works, pardon? Add a row with Brad and, good point. Well, no, it's not because, oh, I see what you're saying. Now we're adding, okay.
If the subject-
Yeah, William's point is if I add something that's not in, yeah, that's right. William's got a good point. So the reason I'm doing the join here is there can be extraneous tuples that are getting, that the join's getting rid of. So I might have extraneous ones like Glacier National Park or Redwood that doesn't matter. So in that case, I do need the join. Thank you, William. Okay, other questions? Okay. So that takes care of all of our 8 operations. So we've looked at the notation essentially for the the 8 operations. Then there are aggregate operations, and of course we have to use all kinds of crazy looking symbols to do it. To me, this looks like a script T, and this looks like a script P. Someone maybe can tell me, is this some Greek letter? Tau, maybe? One of you know Greek? Surely this must be a Greek letter.
The first one is the pro.
Is pro?
Pro.
Pro?
Pro.
Okay.
The that one
Doesn't ring a bell?
Yeah.
Someone else had a?
It's Frank script
Frank?
from the old German.
From Old German. Thank you. So, very, okay, someone had a sense of humor. Okay, everyone. So this could be pretty hard to do on your homework. I'd be happy probably with a T here and probably a P here. So if you're doing an aggregate operation, this indicates that you're applying the aggregate operation. Down here you put the list of your aggregate functions attributes. Over here is what you name them. And you get the 5 that you already know about. So here's an example. Here we are counting the number of properties such that the rent is greater than $350. And we're naming the resulting column my count. So it's the same as saying select count property number, which I'll abbreviate, as my count from property for rent, where rent greater than $350. Okay, and then if you want to group, then you put the grouping attribute to the left first. So here we're saying that here's our 3 names for our 3 columns. So the 3 columns should be named branch number, my count, my sum. We're grouping on branch number, so that's the subscript before the T. Then afterwards, we're counting staff number and summing the salary for the staff. So we're listing the number of staff working in each branch and the sum of their salaries. You'll notice branch number did not appear here, but it appeared here. So anything that appears in this set of columns must either have appeared in the grouping by clause or be one of the columns computed by the aggregate function, which is just what SQL, same restrictions that SQL applies. Okay? Questions? It's pretty straightforward. It's just a matter, when you do the homework, of looking up the notation. Okay. So, we're done with relational algebra. Again, relational algebra is very procedural. It's telling you, in many cases, exactly in what order to perform the operations. So going back, here it's telling you perform the selection first, then do the semi-join. I could have done the semi-join first and then done the selection. So relational algebra is very procedural. It's essentially saying do the operations in a specific order. The relational calculus, higher level, it's only saying what you want. Okay? So, what you're going to do with the relational calculus is you're going to present essentially a predicate, such as salary greater than 150,000. So a predicate might be something like salary greater than 150,000. Then what you're going to do is you're going to instantiate this predicate with certain values. So for example, each employee's salary will be plugged in here. So one employee's salary might be $80,000. So you plug it in, and once you've plugged it in, it's now called a proposition. So when we substitute values for the arguments, we get a proposition, which will evaluate to either true or false. In this case, it evaluates to what? What does it evaluate to? False. Okay? So that's essentially, basically the where clause in SQL is the predicate. And then when you say select from, so typically you're saying select something from some relation R where predicate. So what's happening is for each tuple in R, it's substituting the values for that tuple into this predicate, and when that proposition is true, the tuple goes into the result. Make sense? Okay, so it's not that hard. Try to keep it concrete. Okay, so this is called the predicate calculus. Don't believe me, when I first saw it as an undergraduate, it terrified me. It sounded very complicated, but this is a lot easier than actual calculus. This is more like simple Boolean logic over sets. Okay? So don't let it get, it's almost like they gussied it up. Like the person who founded it thought, wow, this is easy, but I want a research paper out of it. I know, I'll call it calculus, and then everyone will be impressed at how hard the research result must have been, and they'll publish. Okay, so don't let the word calculus be off-putting to you. Okay. So when a predicate contains a variable, such as salary, there has to be a range for it. That range can either be what's called a domain or a tuple. We're only going to worry about tuples because that's what SQL uses. So there's two forms of the relational calculus. One's called the tuple calculus, and one's called the domain calculus. We'll worry only about the tuple calculus. And what that means is the tuple calculus says that the range is over the set of tuples in a relation. So the tuple calculus says that variables in predicates range over the tuples in a relation. So that's specifically bound to the, or circumscribed by the set of tuples in a relation. Okay, so basically what we do is for each tuple in the relation, we substitute the values of the tuple into the predicate. If it's true, that tuple ends up in the result. Okay, but there's no indication of how you have to do it or the order. Just you figure out whether it's true or false. Okay, so we call, in the tuple calculus, we call our variables tuple variables. And we specify them this way. So we're saying that the tuple variable S ranges over the tuples in the relation staff. Okay, when you say select star from staff S, you're in effect saying S is a tuple variable that ranges over the values of staff. Okay, so then the relational calculus, you apply some predicate to each tuple in staff, and the set S is the set of tuples where this predicate is true. Okay, so here's some examples. So this particular one is saying we want the set S such that S is in staff and S dot salary is greater than 10,000. So we're saying list all staff whose salary is greater than 10,000. And conjunction is this is an and is the up, or is this V, and not is usually written, I believe, like that, or like this. Okay. And if we want a particular attribute, so this says list all attributes. This one says only list the salary in the result. So basically, your projection occurs on the left-hand side, so that's your projection. And your selection is the predicate. And these are your tuple variables. So the from clause is your tuple variables. So I'm just kind of mapping SQL, what you see in an SQL statement, to what you see in the relational calculus. Okay? So, oftentimes, if you're having trouble expressing something in the relational calculus, say on the homework or an exam, try writing it out first in SQL and then see if you can't translate it to the relational calculus. So if I might say, I don't know how to write the query, find the salary of all staff earning more than 10,000, try writing it as an SQL query first. There we go. And then you know, based on what Dr. van der Zanden said, that these go to the left of the bar because they're the projection. These must be my tuple variables, and this, whatever is here, must be my predicate. And sure enough, this maps to the left side, this maps to a tuple variable, and this maps down to my predicate, which is conjoined with a conjunction with the tuple variables. Okay? So it really helps often to be concrete and then go to the abstract. Some of you who are comfortable mathematically will feel comfortable just going straight to the set notation. Others of you won't. This is, I think, a helpful intermediate step. Okay, so it would be pretty weak if all you had was predicates. Remember, the first day we talked about SQL, we talked about single relation queries, and all we had was select, project, and aggregate operations. And the second day we talked about multiple relation queries. So if all I give you with your predicates is conjunction, disjunction, and not, or negation, you only get single relation queries. So to get to multiple relation queries, you introduce two quantifiers. One is for there exists, and one is for all. Okay? And tuple variables that get qualified by for all or there exist are called bound variables, and otherwise they're called free variables. And only free variables can occur on the left side of the bar. So let's go straight to an example. So I want to list all tuples and staff. I want to basically list all staff who work in the London branch. That's what I want. Okay? So in order to find all staff who work in the London branch, I'm going to have to look at two relations, the staff relation and the branch relation. So the free variable is staff. I only want staff. So actually, what kind of join is this? Based on the 5 I gave you earlier. What kind of join am I asking for? Is it a theta join? How many think it's a theta join? Okay, how many think it's an equijoin? How about a natural join? Okay, how many think it's a outer join? And how many think it's a semi-join? Okay, we didn't have enough voting. It's a semi-join because I only want the tuples and staff. Notice if you look at the left-hand side, there's nothing in there from branch. So that's a semi-join. Only the attributes from S participate in the result. So staff S, the S variable is our free variable. What gets bound in this case is the branch. So we're saying that a staff belongs in the result if they're part of the staff relation and there exists a branch B such that B is in the branch relation and that branch number matches the staff's branch number and the city is equal to London. So in this case, the branch is the bound variable. Okay, it's not free. It can't appear on the left-hand side. So we're basically saying we're only going to select a staff member S if we can find a tuple in B that satisfies this predicate. Okay, here's one with the universal quantifier. So we are saying in this case, for all B, B is in branch and B dot city is not Paris. So this might be, for example, a integrity constraint where we want to ensure that we don't have any branch that is in Paris. Okay? Or we might be looking for any staff who is not in Paris. So we might be wanting all staff who are not in the city of Paris. Okay. So I found the book's interpretation of for all confusing. This is the way I think of it. So for all B, it means that for every tuple in B, this predicate must be true. If it's false for any, if for even one tuple in branch, this predicate is false, then the whole thing becomes false. Okay, and De Morgan's laws apply, so you can invert the meaning of for all to mean there does not exist a branch B such that B dot city is equal to Paris. And you can do the same with exists. You can invert it using De Morgan's law. So whichever way you think reads more appealingly is fine. Okay. I want to go ahead quickly to something. Okay, so this is a comparable query to the one you just saw. It's just slightly different. This is list staff who manage properties in Glasgow. So it's saying it's a set S such that S is in staff, and there exists a property such that P is in property for rent, and the staff manages that property, and the city is Glasgow. Now, if you wrote it literally like this in SQL, it would look like this. And does anyone remember, this is a subquery. There were three types of subqueries. There were scalar subqueries, there were table subqueries, and there were row subqueries. Does anyone remember what one this falls under? Okay, it's actually row. Table is where you use in. Row is where you use exists. Okay, so if you literally translated this query into SQL, it would look like that. Now, that's not how I would probably write it. I would probably write it as a join. But you will see as we go through our examples that the reason subqueries exist in SQL is because joins do not exist explicitly as an operator in the relational calculus. In relational calculus, everything is accomplished using subqueries. Nothing is accomplished using a join. So let's head back. Okay, so if we're talking about how you can build up formulas, so the atoms are formula that are either tuple variables or have a comparison with some between two attributes, or that are compare an attribute with a constant. So there's basically three kinds of simple formula. Ones that specify a tuple variable, ones that specify a simple predicate between two attributes, and one that specifies a predicate between an attribute and a constant. So very simple formulas. Then you're allowed to combine them using the Boolean operators. Okay? In relational algebra, they're called conjunction, disjunction, and negation. In Boolean logic, they're called and, or, and not. So don't be misled. Conjunction is simply and, disjunction is or, negation is not. And then if f is a formula with a free variable x, then you can bind that variable using either there exists or for all. And now that resulting formula is also a formula. So those are the basic rules for constructing formulas. So it's very simple. This is a very simple set of rules for setting up formulas. They're either predicates, tuple variables, a combination of predicates using Boolean operators, or a binding of a predicate using there exists or for all. So there's really only 5 forms. It's pretty simple. Okay? And you can map it pretty easily to real SQL. So Boolean operators are typically used for select queries. Okay, so they're typically in the where clause. Okay? There exists X such that some formula is typically used for joins. So that's really a subquery in SQL, but as I said, there is no explicit join operator in the relational calculus. The way you get it is by using a qualified formula with there exists. For integrity constraints, you're typically using either there does not exist X or for all X. And these are the same. Why? For those of you more mathematically inclined, those two are comparable. Anyone remember why from 311?
It's not existent for all or and for all are not exists not X is always the same as for all X.
Right.
And similarly.
And who's the famous person who said
Morgan.
the Morgan? Very good. The Morgan's law says that these two things are the same. The Morgan's law says those two are equivalent. Sorry, Dan, I didn't mean to put you through the whole thing. Those two expressions are equivalent. Okay, so those two formulas are both, so the first one says all staff members must make less than 100,000. The second one, but I could equally well say there does not, for one, I could equally well say there does not exist a staff member who does what? Who what? The opposite. What's the opposite? Okay. First one is this one. I'm going to make someone say it. Who makes more. There does not exist a staff member who makes more. Slightly wrong. Or equal to 100,000. Okay. I left out exactly 100, but you get the point. Okay. Also, union, difference, and intersection do not explicitly exist in the relational calculus, but you can express each of them via an appropriate way. So here, I'm listing all cities where there is either a branch office or a property for rent. And you'll see something unusual. I say it's the set T dot city. Notice on the right-hand city that T doesn't range over anything. Kind of strange. That's when I have trouble wrapping my head around. So T is not ranging over anything on the right-hand side. Instead, I'm saying that either there exists a B such that B is in branch and B dot city equals T dot city, or this is the disjunction, or there exists a property for rent P and P dot city equals T dot city. So basically, I can list any city that I want over here on the left-hand side, but it's only going to be legitimate if it matches either a city in branch or a city in P. So this is the one time where you actually have a variable on the left-hand side that's in effect unconstrained on the right-hand side. Okay, in pretty much every other case, you will see the variable on the left-hand side constrained on the right-hand side. So set difference, if I want every one where I have a branch office but no property for rent, now B is the free variable, and I'm saying there does not exist a property P such that B dot city equals P dot city. So that's set difference. That makes sense. An intersection says it has to be both a branch office and a property rent in the same city. So now, again, it's the cities in B that also have a property for rent in that city. So now, instead of saying not exists, we say there does exist a property P such that the property city is the same as the branch city. Okay, so that's set union, set difference, set intersection. Okay, and here's set division. So I'm just showing you how you can translate essentially each operation in the relational algebra into the relational calculus. So I'm giving a kind of quasi-proof that the relational algebra is relationally complete. So here I'm assuming that tourist has some tourist information. Visits is which tourist has visited which park. Park is a list of parks in the state they're located in. So I want tourists who visited all parks in Tennessee. That's set division. All parks in Tennessee. So the free variable is tourists. and for all parks, I have either the park state is not equal to Tennessee. So if the park was in Colorado, I don't care about it. I don't care whether the tourist has visited a park in Colorado. So if the park state is not equal to Tennessee, that's fine. Otherwise, if it is a park in Tennessee, then there must exist a visit, V, such that the tourist is associated with that visit, and that visit is associated with that park. So it's a kind of odd way of writing set division, but it works. Either the park is in Tennessee, in which case there must exist a visit for it for that tourist, or the park is not in Tennessee, in which case it easily satisfies the predicate. So that set division. Again, you'll probably have to look at these, not claiming that it's super intuitive. So now a bunch of examples to finish off. So here, list the names of all managers who earn more than 25,000 pounds. So I only care about the first and last name. The staff is an S, the position is manager, and the salary greater than 25,000. Okay, we already went through this query. Now, actually, here's a common mistake. So this is the right way to write the query, staff who manage properties for rent in Glasgow. So it's a semi-join. This is the wrong way to write it. It seems like it's right. S is in staff, P is in property for rent, and P dot staff number is equal to S dot staff number. This looks like a join, right? That's how you write joins in SQL, essentially. What's the problem? There is a problem here with this query. Well, it's at the bottom. P is a free variable, but P does not appear on the left side of the bar. Okay? If it's a free variable, it must appear on the left side of the bar. Otherwise, it must be bound. It must appear to the left of the, and if it doesn't, it's bound. Yes?
You're just saying that if, like, S appears in multiple parentheses, which means it must be defined on the left side of the...
What do you mean S appeared in
Like
multiple?
P is not defined while S is defined.
That's right. So S appears over here, and therefore,
If it's in multiple parentheses, then it must be defined on that left side.
what do you mean in multiple
Now you're
parentheses?
saying it's a free variable, so it's used throughout the...
No, a free variable is simply one that appears on the left side of the bar. That's it. It can be a free variable if it's on the left side. If it doesn't appear on the left side of the bar, it must be a bound variable. So this is an illegal statement because it doesn't appear on the left-hand side.
Okay.
However, go ahead. Yes, so this was the right way to write it. So this query this is the right way to write that query. And now I've bound it. So I've said, and there exists a P such that property for rent and P dot staff number equals. So this is the correct way to write that query. Because now I've bound it, like you said I should. Okay. Now I get to write it directly. Here, P and S appear on the left-hand side. Now it's more natural because I can say staff S and property for rent P. Now I can say and P dot staff number equals S dot staff number. And the reason I can say it is because both S and P appear on the left-hand side. I think that's silly, but I don't make the rules. Okay? And I never got to talk to one of the mathematical geniuses that decided this was illegal. But they said it's illegal, so it's illegal. Okay? Here is how I list the names of staff who currently do not manage any properties. So the person is a member of the staff S, and there does not exist a property P such that P is in property for rent, and the staff member manages that property. Or alternatively, I could say S is a member of staff, and for all properties, the staff does not manage the property. Okay, I'll let you go through. Here's the last slide I want to go through. You can't have an expression that generates an infinite set. So this looks valid to set S such that S is not in staff S, but that's an infinite set, right? You can make up any tuple you want pretty much as long as it's not in S. So that's not considered a valid expression. So we add the restriction that all values in the result must be values in the domain of the expression. The domain of the expression is staff S. Therefore, we would say that this is equal to what? If we restrict it to be all values in the domain of S. Empty set. Because there are no, if we restrict it to be members of the staff S, there are no people who are not in S. Pardon? There you go. Okay. So that does it. On Thursday, we're going to start 2 weeks of design. So we've kind of gotten through the theoretical foundations of relational databases and the concrete SQL. Now we move into designing relational databases for the next 2 weeks.